Good afternoon, everybody. First of all, I'd like to say thank you to Dongbu High Tech for organizing the forum, and especially for their hospitality. Really appreciate it. I'm with Connection Systems. Connection is based in Southern California, in sunny Irvine, and I run the audio business. Connection primarily focuses on two businesses now, audio and imaging. My talk today is voice interaction comes of age, controlling our consumer electronic devices via voice. And uses of voice. Voice is now becoming increasingly a large part of the consumer's everyday electronic experience. We expect when we make phone calls that the quality of conversation is very clear. Also, same thing for video conferencing. Voice input as a replacement of typing Google. We want to say Google and it comes up as a web browser, for example. Voice control. This is a newer market, and the Korean companies are dominating this with Samsung and LG, where you can talk to your TVs. You can say, "Hi TV," and the TV turns on. So as you can see, voice is ubiquitous. It is everywhere. And I've just put a few applications, and I'll go through them so you can get a better understanding of how we use voice to enable different functionality in this application. In smart TV, you can use voice control to turn on and off the TVs. You can use voice to search. I say, I want to watch a movie, it'll go find it for you. And last but not the least, it's a big screen, the TV. You want to use it for video conferencing. You can enable it by using Skype. Again, it has complications, difficulties that I'm going to talk to you about later, about how we overcome that. Appliances, again, in Korea, we have a couple big customers here where they have the very high-end air conditioners, where instead of using a remote, you can talk to your air conditioner and say, turn on, and it will turn on, and make it colder, and it will turn colder. Gaming is an area where now 2 out of the 3 largest console makers have now put voice chat and voice control in the market. So therefore, give you a much richer experience when you're playing. Microsoft first originally introduced it with Kinect, where they not only put gesture but voice in there. I believe there are other companies also working on that. So this opens up a new market of voice interactive games, where I can have a game where I can talk to it, somebody on the other side can hear me what I'm saying. Okay? We've been using voice in automobiles for a long time. We use it for hands-free. More and more countries don't allow you to hold your phone and drive. So the hands-free function has become very important. For hands-free function to be important and to work, it needs to have noise cancellation. It needs to have echo cancellation. That's some of the technologies that we are enabling. And obviously, you want to be able to not click the buttons, say turn on or call Kevin in this case, and it will do that on its own. So that's another great example of voice. Everybody knows and uses voice in smartphones and tablets. Our virtual assistants like S-Voice or Siri have already been enabled, have been around for a long time. And we use it, obviously, we expect clear voice quality when we're on the phone. And last but not least, within the last year in the US, some of the set-top box makers like Comcast are now also introducing voice-enabled remotes, where instead of picking what movie you want to watch, you just say, I want to watch this movie. It goes, searches, and do it. So as you can see, voice interaction is becoming important. It needs to work well. Okay? So since the dawn of civilization, humans have sat near a fire and have talked. And this is the mode of communication that we are the most comfortable with. Now, only if our electronics listened to us and understood us, it would be better. But the electronics are like our children. Maybe sometimes they understand us, sometimes they don't. So we're trying very hard to improve that experience so it understands us most of the time. And as I said, voice again was very easy to use. It's been around a long time, but unfortunately, we haven't deployed it, mainly because it's been very difficult. There are many limitations to that technology. And that is why we still use a point and click. We use remotes, we use our mouse. Many other ways to communicate with our electronics, right? So I'll spend a little bit of time talking to you about voice input and control and some of the evolution of it. Voice input and control really requires high performance speech recognition. Prior to 2008, there has been speech recognition engines that have run on your PCs, but unfortunately the computing power was not adequate. And they really only supported very few commands like dictation or voice input with limited control. But in the past 5 years, we have seen a huge improvement in this technology, mainly driven by cloud-based server, speech recognition engines and large bandwidth. This has really allowed unlimited natural language voice input and control. So the market now really supports both cloud and local engines because cloud by default has some latency. It has to go out back to the cloud and come back. Local, on the other hand, is running right there. So most of the technologies out there take a mix of both cloud and local-based technologies. So just to discuss some of the basic commands, so some of the examples of voice commands that are available, the basic commands really only require limited speech recognition, and these are mainly done locally, where I say TV on or phone on, which is they're always listening, channel up, channel down. Those are the ones that we do locally. Natural language voice input and control really requires a higher performance speech recognition engine, which really offers true natural language speech interface, where I want to go say, I want to watch Minority Report on Netflix. I want to say that to my TV, or I want to say that to my smartphone. It goes to the cloud, processes this information, and comes back. Same thing. Can you recommend me a Mexican restaurant in Irvine? It'll tell me the El Torito's is next to the Connexent office. So go and eat at that. But for the cloud-based speech recognition engine to understand what it said, it really needs to pre-process that signal. And that is what Connexent does. We pre-process the input that goes into the speech recognition engine. So this will give you the performance that you need. Because otherwise, if the speech recognition engine is unable to understand you, it doesn't matter what the output is. We therefore pre-process the information, and as you can see, I'll show you the chart later, it therefore allows much better understanding. So in natural language voice input and control, the engines are becoming very powerful. We are all familiar with Siri from Apple, or S-Voice from Samsung, or Q-Voice from LG, Google Now. These are some of the examples that use natural language voice input and control. But as this lady is here with the phone very close to her, this is what we call near field. And near field, you guys have mostly used it. You'll find that the performance is pretty good when it's in a well-controlled environment. It's not in a big room. It's not in a Starbucks. It's pretty good. It works really well. And that's what we call near field. But the challenge with voice input and control is they tend to fail or become unreliable when they're used in the real world. As I said earlier, near field works really well if I'm holding it. So for all of us not to become like him, which is screaming to the phone because it doesn't understand us, we need to overcome these limitations. So the other definition that I'd like to share, one is near field, the other is far field. Far field is when I'm sitting here 0.5 meter to 5 meters, where it can still capture my voice, but there's a lot of interference from the environment. And reverbs, which is the room size, which will cause a lot of interference, and the signal is changed. It really degrades the ability of the natural language speech recognition. So overcoming these limitations is really, truly necessary to realize the promise of natural language, natural voice recognition. So as you can see, near field, as I said earlier, works better. Far field is a challenge, and that is really, if we solve that, people will start to use this technology even more. So as I said earlier, how do you enable this in the real world? Mitigating environmental noise and interference is the key to natural language voice input and control in the far field application. So as you can see, if I'm speaking on a phone or talking to a TV in a room, speech plus interference looks like that. It could be, if I'm talking to a TV, it could be a baby crying, a dog barking, my air conditioner running. If I'm talking on a phone in a loud place, there's a lot of people talking, there's a lot of noise going on. What we do is we take that speech plus interference signal, which is a very noisy signal, we pre-process it, make it a clear speech, and then we are able to send that signal to the speech recognition engines. If you send this signal to the speech recognition engines, it will not work. It will give you the experiences that you've had, which are bad experiences. And as you can see, more and more technologies, the new watches that are coming, there is no buttons. You need to talk to it. And for that to work, this signal needs to go in. Google Glass, which is the new glasses that you have to wear, again, there are no buttons. You need to talk to it. So that is the technology that we'd like to enable. So therefore, you can see for Skype calling, or even your tablet, or even a watch, you need to have that signal. And the same thing, the similar type of signal then goes to a speech recognition engine, which will really increase the accuracy of your voice input, your voice control in your system. All right? So again, it's what we call in the far field, it's what we call for real-world conditions. So putting it all together, smart audio from Connexent is really what is trying to put all of this together. And our solutions are our audio capture and processing algorithms, our high-performance mixed-signal components that we are working with Dongbu on, also a low-power DSP, because a lot of these systems are always on, are always listening, so they really have to work on low power. We also have additionally some playback on the back-end side, where if you get a call and you're in a noisy area, it increases the volume on its own. Few of these experiences. So we put it all together to really provide you a rich audio experience. So as I said, Connexent really enables a turnkey integration of high-quality voice pre-processing for all consumer electronic devices. We offer a portfolio of solutions for clear voice communications and voice input and control. Okay? I'm going to talk a little bit about pre-processing to enable voice communications and natural language and control. Give you a little bit of history and some of the technologies that are behind it. So a little bit about genesis of Connexent's technology. Voice and speech recognition is old technology. It has been around a long time. And it's really primarily at Connexent has been originated in research in natural language pre-processing for far-field communications and speech recognition. As I said earlier, we define far-field as a user who's 0.5 meter or up to 5 meters away from the microphone. 5 meters is quite a challenging distance. And originally, our first two big market targets, because the 5 meter, was smart TVs and appliances and other smart home and gadgets. And now we are also focusing on hands-free for cell phones to really give you a truly full duplex communication. More and more people are using their mobile phones as speaker phones, and we want to be able to enable that technology. And as I said earlier, the far-field scenarios impose multiple challenges. Interference can be at the same level or even higher than the desired signal. This is a challenge, especially if somebody is speaking a lot louder. How does it know it to capture me? So this is what we call beam forming technology. The beam forms to me, and then I'm able to do it. Room. If I move my furniture in the room characteristics change. So our products need to adapt for that. That's what we call reverb from the room. Distorts the signal, which can have really a severe effect on speech clarity and how well the speech recognition engine works. Dynamic range of a desired signal can be very large. TV is a perfect example. If the TV is on, it's very loud, and I talk to the TV, it needs to forget what the TV is saying and listen to me. So we need to suppress that signal, take our signal, and take it. So again, this is where all the pre-processing is important. And our solution really is designed for these challenging, real-world, real-life examples. This is a little bit technical, but I said, we've got some technical people here. I'll talk a little bit about the algorithms that we have looking at. So there are really two different ways of pre-processing. One is what they call is a blind source separation. This uses a statistical independence to decompose the acoustic scene into their atomic sound components. This is what it says, is that it looks at each audio signal or acoustic signal as a separate and individual item and a separate event. There's another theory called CASA, or computational auditory scene analysis. This attempts to model the human ear and the brain. So as you can see, one would think, well, maybe the human ear is a better way to go. But you must remember, we are communicating to compute platforms. Phones, TVs, everything is by default a computer. So therefore, BSS, and I'll talk to you a little bit about that, is a better method for the recognition to work. So as you can see, humans and computers, as we know, are fundamentally different. Humans can integrate multimodal information, that means audio, video, all at the same time. Computers can only do it in single modalities. Humans are continuously learning and organizing the information. Computers cannot access a lot of memory because of limitation. Humans can do simple operations, but many at a time, while computing can do a quick, structured, complex mathematical operations, but with limited amount of parallelism. And finally, humans have experiences that we bring in, or exemplars, as we say, while computers really look at it in mathematical models. Connection implements a BSS, or blind source separation, modified for real-world robustness. This is why, because we optimize for the computer's intrinsic attributes to enable these capabilities, meaning what you're talking to is a computer. And therefore, it is better to use this technology as opposed to this technology to enable this feature. Okay? So as I said earlier, we use blind source separation. Our algorithm is really based on a multi-channel blind source separation theory, and I'll show you a demo right after this. We overcome the robustness issues by putting a little bit of real world in there, and we do not attempt to model the human ear while we dynamically model the acoustic environment. Okay? So, as I mentioned earlier, by using the computational method of BSS, we call it our superhuman capability. So, what I'm going to show is an example where you'll see 5 voices in a real room. There are no visual cues, language or knowledge. So a human being, and you will listen to it when they play it, no, not yet, and you will not be able to differentiate those 5 voices. But our solution, by using a dynamic acoustic scene model, will detect and separate these 5. So please go ahead and play this side first. Yeah. So as you can see, I don't think you could tell how many people were there. The language you could tell is Italian because our main researcher is Italian. So he insisted on putting Italian in there. He's an expert in blind source separation. He's from Italy. And now let's, as you can see, if I was even a human, I could not have understood a single thing. And this is what happens at a Starbucks or a cafe, right? So now let's go ahead and play. So now we're able to separate each 5. So there are 5 different ones. Now there is a little bit of artifacts. You can hear it. It's tinny, but at least on the other side, so this then goes to a speech recognition engine. You can play a couple more. The engine will then understand it. So that's why nobody. So as you can see, we took with 2 microphones. I think that's fine. Thank you. So we took 5 different people speaking in 2 microphones where they all look the same. And even if we were standing there, we could not have understood who's saying what. And we were then able to separate using a dynamic acoustic scene model, using our algorithms and our ICs into 5 different audio streams. Then these audio streams can go and work, okay? So in addition to that, we are enabling better call video conferencing quality, natural language voice input, and our approach really adds a few more other very important things. We give a very low-cost, small footprint, as I said, a implementation using as few as 2 microphones. There are systems out there and solutions that use 4, 6 microphones. We can do this by 2. We are the first ones to enable this with 2 microphones. Another thing, orientation independence. This is very important. As you can see, the new tablets have 2 microphones. You move it, the quality changes. We take care of that. We are able to work around that and make sure that the quality is still good. Distance and location. If I walk around like I'm walking around on a tablet, it will sound very bad. It will work or won't work. But with our technology, you'll get excellent voice clarity when the user is far or moving from the device. So as I'm walking, it is adapting and learning. It's adapting and learning. And then, as I told you earlier, the noise environment. We reduce both ambient stationary, which is one place, and a non-stationary, like a car that might go, regardless of the user position to the device. So very important. We put all of this together in the technology that we did. So I talked a little bit about the algorithms, the software, the firmware, the genesis of that goes into this market. Now I'm going to spend a little bit of time really talking about the silicon that enables this. And this is not, we really had to work on a very high fidelity ADC that we are working with Dongbu on, and a low power DSP. Without the high fidelity ADC, this technology would not have been enabled. So as you can see, this is our latest product, the Nebula, which really is a standalone subsystem, which is a far-field voice input processor with an integrated acoustic speech recognition engine. As I said earlier, power is very important because these systems are always on or always listening. So this really provides you the lowest system power wake on voice. So when I walk into a room, I say, hi phone, and it turns on. So this is why power is very important. It allows for command buffering where I can give multiple commands and our chip is able to buffer them and therefore understand them. We provide voice trigger assisted selective source pickup. We've got a very large RAM internal into the chip, primarily because we have a lot of functionality, a lot of memory required to do that. One of the big things that you might have seen in this year's latest smart TVs, the microphones cannot be seen. For industrial design, the microphones, our customers asked that we should hide them. This provided a big technical challenge for them, so all the microphones are hidden. But they still need to capture your voice. So our technology, using the ADCs, working with Dongbu, were able to work around this difficult problem, where the microphones are not seen. We also provide the most advanced processing. We do something called super wideband, watch live and talk, where 2 of us can be watching a show together at different places using Skype, communicating about that. And both sides won't hear what we're talking about. And primarily, as you can see, we're able to put this in a 7x7 QFN, very small package. Also, we support CSP for the mobile market. So, as you can see, this whole product is a multiple innovative technologies really integrated into a standalone system. So this is really how it is. Earlier was a block, but it really is 2 very distinct die. The first die is a digital die, which is our DSP processor, manufactured in a 40 nanometer low power LP process, using 1 volt nominal, 200 megahertz, 0.9, and uses a 3.3 volts for the oscillator. ELBA, which is our mixed signal die, which is really 0.18 but shrinkable to 0.16, maybe eventually 0.13. All our IP was in 0.18, 0.16, so we decided to keep it in the same technology this time. And the digital is 1.2 and the analog is 3.3. And as you can see, the digital die is at the bottom, the analog is up here, and they're stacked. Excuse me. And this just shows more of a detailed block diagram. So you have the analog die here, the digital die here. It's got a proprietary interface that allows for very low power, high bandwidth. The processor, the CAPE, is our DSP processor. It's developed by Connexent. It's an 800 MIPS processor, dual core. Each core runs at 200 megahertz with 2 max. We can drive a PWM ourselves. We've got onboard PLL and inputs on this side. The analog die has all the power management on it. Therefore, we can control the digital die from it. It has a DC-DC converter. It's got 2 channels or 4 channels, depending on different modalities and applications. And really, that's really what it is, and we are shipping it already. I'm going to spend a little bit more time on the analog die because that's the one we're working with you on. Okay. So the voice input ADC was very important for this system to work. The reason is we wanted to make sure that we were not the constriction path in this technology. The microphones had to be the weakest link. It couldn't be our solution. So therefore, the ADC really had to be a high fidelity, high performance ADC. And in this case, it's a 24-bit ADC that we have developed. And as you can see from here, it's got a few exciting and new technologies that we've done. We've done a high performance switch cap sigma delta ADC. We've got signal adapting biasing, which really minimizes power consumption. Because as I said earlier, power consumption is very important in this market. We've got transconductor op-amp architecture that really gives you a low noise for a high input impedance. In addition, we also have a low noise microphone, differential inputs, and last but not least, all our customers don't like to put external components. So our architecture allows them to minimize external capacitors or resistors in the space. So therefore, you can see it was a very unique product that we developed just for this voice capture market. You cannot take a standalone ADC, because there are many ADCs out there, or analog to digital converters as they're called, and put it in the market. You needed a very specific one designed for this area. So as you can see, our preamp, the green line shows you what the competing solutions are. The red line shows you the Connexent product that's developed with Dongbu. And as you can see, this is the microphone limit. So why did we design this way? So as you can see, the noise level for ADCs is lower than the intrinsic noise level for the microphones. So the ADC had to be lower than a microphone, even at a low gain. The existing products out in the market at low gain were much worse than the microphone. Therefore, they were the long pole in the tent. This way, using this technology, high gain in the preamp is unnecessary. So we can even, with a preamp gain of 10, we're still able to meet or exceed the spec of the microphone. Therefore, why is using low gain important? Allows you not to saturate your microphone, okay? So in conclusion, as you can see, this technology had not only DSP algorithms, but a very high performance ADC that goes with it. So really, the applications are very broad for us. Our solution was born as a far field solution. Personal and near field are simpler problems for us to solve, really. We provide superior performance with a high SNR gain with speech distortion. So really, some of the applications right now are smart TVs, mobile computing, appliances, and communication. And really, we provide call clarity, natural language voice input in millions of products. I wanted to just show you a real-world example from a TV. So could you please go ahead and play this one first? So there's a person talking, and you cannot hear that person. So there is no processing going on right now, and this is what the signal in reality in a room would sound like. Okay? Now so this would give you 100% failure for speech recognition. Our customers told us, you got to pass this, because this is the real world example. It was 100% failure of speech recognition engines. After we did our processing, so as you can I think that should be it. So we really had a lot of work to remove all the interferences and decide what this is. So the other technology that I didn't talk a lot about today is beamforming. So the beam would come and focus on you. So really, what are the future applications? You know, call clarity, natural language, voice input and control. I talked to you earlier about all these new modalities coming up require us to talk to them. There is no buttons, there is nothing you can hit. You really have to talk to them, and they really need to understand us. The new technology that's really we are working on, which is very exciting, is something called contextual awareness enables a new intelligence. This is when I say open Facebook, it opens my Facebook page and not your Facebook page. So this is the next level of this technology that we're working on, where we need to be able to tell who the speaker is, in what context I'm speaking. So that's the next area of technology. And of course, there's more that goes with this. You know, voice, I believe, is just starting as a market, and it's really going to explode as the applications and the usability of it happens. Thank you. That's all I have.
Thank you very much.